Pretty slanted. All right, welcome to part two. Realized as I was turning it on, you probably heard me. Very slanted matrix, so you gotta love the end of the day, about to fall over writing this on the board. So part two, I decided after looking through it, I think this will be put into three parts. Just want to highlight, if I was to look at the original matrix A, that could be transformed into this reduced row echelon form. We want to talk about the different spaces for this matrix, what's the same and what's different and why. Now the book does a great job, most of it's explanation based, and so I really just wanted to compare the two, kind of point and kind of give you some visuals, just to kind of aid again if you're just kind of going with the book. And again, do as best as I can in terms of the perspective. And if you have some more clarifying questions, please let me know, again, from the text or from this discussion now. And so when we're looking at let's start with the row space again. I want you to notice that when I'm looking at this matrix, this last row, if this is the original A value, this last row is gained by adding these two rows together. So that's why this creates ultimately the zero row. But in the long run, when I perform these row operations, when I perform the elementary row operations, they don't change the row space at all. In other words, when I go through and I find the row space for A, it is the same as R0. The space itself is the same. So the column space of A transpose is actually the same as the column space of R transpose. They don't change at all. And it's just because of, again, these first two rows are independent of each other. The third one is dependent, so this would have a dimension of 2, and the vectors themselves are the exact same. Anytime you perform the row operations, it does not affect the row space. What can change, and this is where we get into column space in particular, is the column space for A is not the same as the column space for R0. And so that's what I do want to write up here. These two things are not the same. The basis that would create the column space for R0 can be different than the column space of A. So we don't want to say that they're exactly the same, but what I can say is that the dimensions of these two spaces would have to be the same. So the dimension here would always match. And that's what you'll see listed in the book in terms of, if you pay really close attention to the wording, that the dimension of the column space for A is equal to the dimension of the column space for R0. But again, the actual spaces themselves, if we were to take into account all of the linear combinations, don't necessarily have to match. And I think this is where the visual comes in handy, because when we reduce this matrix to reduced row echelon form, we can identify what my independent vectors are. So when I'm looking at just R0, I want you to notice how it's essentially looking at the identity matrix of 1, 0, 0, 0, 1, 0. This would be the XY plane and three-dimensional space. Well, if I look at the column space for A, the column space for A are these two independent columns. Well, because this had zeros on the bottom because of the reduced row echelon form, this does not. So this created a plane that's exactly the XY plane. This actually allows us to go through and do combinations to get an actual Z, and forms a different plane in R3. It's not the XY plane. And so notice that if I find all the linear combinations of these two vectors, it does not give me the same space at all. But the number of vectors in the basis match. And that's the takeaway. That the dimension of the column space, if I go to A or R0, always matches. And so that's why when we go through and we're looking here, just to go ahead and identify this on page 133, the fundamental theorem of linear algebra part 1, the column space and row space both have dimension R. Those dimensions can never be different, but the column spaces can be as we're changing the matrix. The row space will not change because elementary row operations will not affect it. And so that's one of the first things I really wanted to kind of highlight. The second thing that I want to highlight is when we're looking now at the null space for this, when I'm looking at the original matrix, the null space is the exact same as R0. In other words, the solutions that we found here are the same exact solutions here. The basis matches. And so the space itself, whether we're finding the null space for A or the null space for R0, it's like the row space. It's exactly the same. Which is kind of really interesting when you're paying really close to the subspaces and how we're looking at the same subspace and how those are equal, not just in dimension in terms of the null space of A or the null space of R0, but in terms of what they're looking at. So seeing kind of that connection there. Versus the column space looking at Rm, that subspace is different when I'm comparing the two. And one of the things to kind of notice with this, and this is kind of the second part, they call this the counting theorem, is that if I found the rank of the matrix, which is the dimension of the row space and column space, well, if I add to that the dimension of the null space, this is always equal to n. This is the counting theorem. And again, we've kind of seen that when I'm looking in terms of the number of columns, that by identifying the number of columns, so identifying the dimension of my column space, the dimension of the null space has to count the remaining columns. And so we kind of see that in terms of the counting theorem. And it works very similar when you look at the left null space and compare that to the row space. And so that leaves us with number 4, which is the left null space of A has dimension m minus r, but the spaces themselves can be different. So it's very similar to when we looked at the column space, and that the space may not be the same between these two matrices when I consider them separately in terms of their basis, but the number of vectors in that basis has to match. And so that's where you have the fundamental theorem of algebra again, give the column space and row space have both have dimension r. The null spaces would have dimensions n minus r and n minus r. The counting rule for A transpose would essentially be, so this is the counting rule for A. I'll put that here, counting rule for A. The counting rule for A transpose would be R plus M minus R gives M. And again, notice how that's essentially connecting the left null space with the column space, Rm, and doing the counting there. And how those are connected. There's an example that's given in the textbook for this, and so I would encourage you to kind of take a look at that. It's at the bottom of page 133. It kind of runs through, it's a 2x3 matrix where the first row, I guess the second row is dependent, it's a multiple, and so therefore there's one independent column because the rank would be 1, and then you have 2 dependent columns, so your null space has dimension 2, and it starts looking at the counting theorem and counting the numbers there, but I think it's very easy to read and kind of follow through. So this video, much shorter, because I want to spend one video just on Kirchhoff's current law, because that's the next example in digging through the spaces. And so biggest takeaways that I want you to have is that we focused on the reduced row echelon form first, but when I go to the original matrix that can be converted to reduced row echelon form, the row space does not change, the null space does not change, the column spaces of the two matrices are different, but the dimensions have to match when I'm looking between the two. Those don't change. And then again, our counting rule in terms of that. So hopefully that helps.